In Chapter 6.1, we are going to expand our knowledge of probability into something called random variables. And the random variables will have probability distributions. So our objectives in this chapter are distinguish between discrete and continuous random variables, determine a probability distribution for a discrete random variable, describe the connection between probability distributions and populations, construct the probability histogram for a discrete random variable. We're going to compute the mean for a discrete random variable. We will compute the variance and standard deviation for a discrete random variable using the calculator. Objective 1. Distinguish between discrete and continuous random variable. So for a random variable, if we roll a fair die, the possible outcomes are the numbers 1 through 6, and each of these numbers has a probability of 1/6. Rolling a die is the probability experiment whose outcomes are numbers. The outcome of such an experiment is called a random variable. So a random variable is a numerical outcome of a probability experiment. We have seen this in our past experience. Well, there are two types of random variables. One is a discrete random variable, where the random variables whose possible values can be listed. The following examples are the number of outcomes up on the roll of a die, the number of siblings a randomly chosen person has, the number of heads on 3 tosses of a coin. Continuous random variables are random variables that can take on any value in an interval. Examples include the height of a randomly chosen college student, the amount of electricity used to light a randomly chosen classroom. Objective 2. Determine a probability distribution for a discrete random variable. So we go back to our rules of probability. A probability distribution for a discrete random variable specifies the probability for each possible value of the random variable. The properties or the rules are the following. We've seen these. For each probability within the sample space, the value of that probability is between 0 and 1. It could be 0 and it could be 1. The sum of all the probabilities in the sample space, or in this case the probability distribution, equals 1. So here's an example of different probability distributions, and we have to decide if they are a valid probability distribution or not. In the first example, x and p of x, here is our probability distribution, supposedly, but when we add it up, it does not equal 1, and furthermore, we have a negative 0.3, which is not allowed under our rules. So this is not valid probability distribution. In our second case, we have x, p of x, and we notice that if we add up our probabilities, they do equal 1. And we notice that all of the probabilities are between 0 and 1. So this is valid. It is a valid probability distribution. The final one, x, p of x, right? Well, we have a problem here. In this particular case, we have a probability over 1. That's not going to work. And again, when we sum up the probabilities, they are greater than 1, so this is not valid. So we're going to compute probabilities under a probability distribution. X is the number of folks that have high blood pressure in a particular clinic, and P of X is the probability of the particular outcome. So part A says find the probability of 2 or 3 folks coming in the clinic having high blood pressure. B is find the probability that more than one has high blood pressure. And then C is find at least one that has high blood pressure. So here are the solutions. The events 2 and 3 are mutually exclusive, and since they cannot both happen, we use the addition rule for mutually exclusive events. So we just add the probability for 2 and for 3, and in this case there's 2 and there's 3. So we add those two probabilities together and we get the probability of 0.35, right? And if we put it in percentage terms, that's 35%. In part B, it says more than one means we have either 2 patients, 3 patients, or 4 patients that have high blood pressure, which again is the addition property because of mutually exclusive events. We would just add the above probability of 0.35 to 0.01, and we get 0.36. Finally, in part C, we use what's called the complement rule when we want to know the probability that at least one patient has high blood pressure. That means that includes one, so we're looking at the probability in this case of all of these. We can either add them up that way, or we can use what's called the complement, at least one, which is 1 minus this probability here, and we get 0.77, or 77%. Objective 3. Describe the connection between probability distributions and populations. Statisticians are interested in studying samples drawn from populations. Random variables are important because when an item is drawn from a population, the value observed is the value of a random variable. The probability distribution of a random variable tells us how frequently we can expect each of the possible values of the random variable to turn up in the sample. In our example of this, we look at an airport parking facility that contains 1,000 parking spaces. Of these, 142 are covered long-term spaces that cost $2 per hour. 378 are covered short-term spaces that cost $4.50 per hour. 423 are uncovered long-term spaces that cost $1.50 per hour, and 57 are uncovered short-term spaces that cost $4 per hour. A parking space is selected at random. Let X represent the hourly parking fee for a randomly sampled space. Find the probability distribution of X. Well, in terms of our probability distribution, here is X. Here's our frequency based upon X. And we can find the probability P of X in the following way. So if we look at 150, the probability of 150, it's the number of spaces costing 150 divided by the total number of spaces. Well, in this case, it's 423 divided by 1,000, which is, guess what, 0.423. And we can do this for the rest of the spaces, the $2, the $4, and the $4.50. As you can see, it is just the frequency divided by 1,000 to get P of X, which is the probability. So now we have a probability distribution, and it's valid because if I add up the probabilities. They equal 1, and the probabilities are between 0 and 1. So here is our probability distribution along with our frequencies. Objective 4, construct a probability histogram for a discrete random variable. So in the past, we have created histograms with frequency data, and now we're going to use relative frequency data, which will then be creating our probability histograms. For example, in the table below, we have the following information. We have the number of boys in a family of 5, and we're using the assumption that boys and girls are equally likely and that births are independent events. So in this particular case, on equally likely events, we can create a model associated with those events. And from that table, our probabilities are over on the y-axis, and our x variables are over here on the x variable, x-axis, and you can see this is our probability distribution. How we calculated the probabilities is like what we did in the last chapter. We looked at the number of ways in which we can select the number of individuals, and we used a binomial case in order to do that. If boys and girls are equally likely, then if we looked at boys entirely of 5 children, the success of a boy is 1/2, and the failure of a boy is 1/2, and so we can generate our probabilities based upon the binomial theorem. So objective 5 is to compute the mean of a discrete random variable. So you will recall that the mean is the measure of center. The mean of a random variable provides a measure of center for the probability distribution of a random variable. So we can now do a new formula for finding the mean value of a probability distribution. It is essentially the possible value of the probability times the value of x. So it's each value of x times its probability, and we sum it over the entire probability distribution, and we get the mean value. In the past, what we did is we did the frequency information in the past divided by the total frequency. And in a sense, it's similar to the probability distribution. So here's our example of finding the mean of a random variable. A computer monitor is composed of a very large number of points of light called pixels. It is not uncommon for a few of these pixels to be defective. Let x represent the number of defective pixels on a randomly chosen monitor. The probability distribution of x is as follows. The mean number of defective pixels, so the question is find the mean number of defective pixels. So this value is x. This is p of x. So that's our probability distribution, and it's a valid one. So now we calculate the mean the following way. We multiply x times its probability. So we multiply these two together. That gives us the first term. We multiply these two together. That gives us the second term. We multiply these two together. That gives us the third term. And finally, in our probability distribution, we multiply these two terms, 3 times 0.1, and we get that term. We add them together, and we get the mean value of 1.2 pixels. So now, if we created a probability histogram, we can see that the center is about right here of our distribution. So in some cases, we want to expand this idea of the mean value to something called the expected value, which sometimes is represented at E of x. So there are many occasions on which people want to predict how much they are likely to gain or lose if they make a certain decision or take a certain action. Often this is done by computing the mean of a random variable. In such situations, the mean is sometimes called the expected value and is denoted by E of x. If the expected value is positive, it is an expected gain. If it is negative, it is an expected loss. So here's an example. A mineral economist estimated that a particular venture had a probability of 0.4 of a $30 million loss, probability of 0.5 of a $20 million profit, and a probability of 0.1 of a $40 million profit. Let x represent the profit and find the probability distribution of the profit and the expected value of the profit. Does this venture represent an expected gain or an expected loss? Notice we use the term expected. So there's x. Here's P of x of our distribution. So we want to create the probability distribution from the wording. And then we calculate. Here's the solution of finding the expected value. We just multiply each value times its probability. So it's a negative 30 times 0.4 plus 20 times 0.5 plus 40 times 0.1. It gives us $2 million gain. So there is an expected gain of $2 million. So the book shows you the actual formulas for computing the variance and standard deviation of a discrete random variable. We'll go over it briefly, but the general idea is that the calculations will be done on our calculator or in Excel. So here are the formulas. The variance and the standard deviation provide a measure of spread for the probability distribution of a random variable. So the variance, in this case for the population variance, is nothing more than sigma squared, which is the summation of each of the deviations from the mean for each value of x. We square that and we multiply it by P of x. Once we have that calculation, we can just take the square root to get the standard deviation. So essentially, we use the calculator to find the mean and standard deviation of a random variable. It's very easy to do. Step 1 is we enter the values of the random variable into L1 and the associated probabilities into L2. So L1 is x as usual, and L2 is going to be P of x, no longer your frequencies. Then what we're going to do is we press the stat key and then we move over to calculate and we select the one variable stats. So we select the one variable stats and then we enter in L1 or L2, and sometimes we enter L1, L2 this way depending upon what your calculator looks like. And then we hit enter and we get the actual results. So you may want to try this on your calculator, right? So we're going to compute the mean and standard deviation of the following probability distribution. So this is the value of x, this is P of x, right? So we're going to enter L1 This will go into L1. This will go into L2 for P of X, and you can see that that's the screen that you do. So when you hit the stats key and hit enter, that's what you're going to put in. Once we do that, we're going to select, we go over to select the one variable, we hit the stats key, we hit the one variable stats command, and then we either have this situation where we enter L1 comma L2, or we put in the X list, the L1, and the frequency list L2, and we hit calculate or enter, and then in this particular case we find the following results. We find that X bar, right, which is mu in this case, is 1.2, and sigma x is equal to 0.872. The calculator does something very interesting in that when he calculates the standard deviation, you will notice that there's no Sx. That is because the probabilities add up to 1. And so 1 subtracted from 1 and minus 1 can't exist. It's an error. So it automatically thinks that the probability distribution, which normally is a population distribution. So in this chapter, you should know the difference between discrete and continuous random variables, how to determine the probability distribution for a discrete random variable, how to construct a probability distribution for a population, how to construct a probability histogram, and how to compute the mean, variance, and standard deviation of a discrete random variable using our calculator. That concludes section 6.1.